dTA, we know that we are measuring the difference in temperature. Okay. Another technique which we focus, first I will go over the techniques, then we will look at the applications. Okay. Differential scanning calorimetry. Okay. So, it is a thermo analytical technique in which the difference in the amount of heat, okay, difference in the amount of heat required to increase the temperature of a sample and reference are measured as a function of temperature. Pay attention. So, here what we are measuring is the difference in the amount of heat, right. To increase the temperature of sample and reference are measured as a reference, as a function of temperature. As you heat it up, right, your temperature will change, like then you want to minimize that. So, you are measuring the heat supplied. Suppose you need heat, suppose it is an endothermic reaction, it is taking heat, so you supply heat, right. So, let us look at what are the common types of differential scanning calorimeters, right. So, one is power compensation DSC, it is called power compensation DSC, right. Idea is here you have a separate sample and reference temperature sensors and furnaces. So, you see two separate sample and reference temperature, sample and reference temperature sensors and furnaces, right, they are separate, and what we are measuring is differential thermal power is measured. In this case we are measuring differential thermal power. Okay. In the heat flux DSC we measure, so here sample and reference are put together in the same, right, they are not separate. Okay. And we are measuring the temperature difference, okay, and then we are converting into thermal power. See, eventually in DSC you are interested in measuring the thermal power, right. So, in this case we are measuring differential temperature or temperature difference and then converting it to differential thermal power. In power compensated DSC we are directly measuring the thermal power. Now, you must be wondering what is the difference between DSC and DTA, right. As I explained, in DTA you have a temperature difference delta T, right, plotted against temperature. Delta T is Ts minus Tr, sample temperature minus reference temperature. Here we have a power dH over dt. Okay. So, here we are directly measuring the power. Okay. That is the difference between DSC and DTA. Okay. So, a few example of DSC. Okay. So, here is a typical DSC curve for polyethylene terephthalate. Okay. So, what happens when you increase the temperature to the heat flow? This is the temperature increase. So, you see some drop, then in the curve stays like this, right. Then you see the peak, okay. This is exothermic peak, then you see endothermic peak. Exothermic means you are releasing heat, endothermic means it is using heat. So, it can tell you what is happening, that is the point, right. You have this DSC curve. So, basically this small drop here tells you it is basically glass transition temperature range, 60 to 70 degrees Celsius, that is the glass transition is happening. 110 degrees Celsius, this one is because of the crystallization, and we know crystallization is exothermic. So, it tells you about what kind of reactions you are, taking place in the sample. 255, then you have melting will need heat. So, you see endothermic peak, right. So, it can give you a lot of information about the reactions. Now, we will go towards the quantitative, how can we use it to measure things. So, before we do that, let us look at, okay. So, this is again a schematic representation of DSC curve, right. So, again you always see when you talk about DSC, heat flow is plotted against temperature, heat flow on y axis, temperature on x axis. Now you see this exothermic peak, right. So now the question comes, what temperature should we use, what is what, right. You see Ti is initial temperature, beyond Ti you see the curve, things are changing. Now you have moved to this, it's no more flat, right, changing the slope. Then you have this linear portion, right. Now if you draw a line like tangent to this and tangent to your initial where it intersects, that is called TE. TE is nothing but extrapolated onset temperature. See, Ti is initial temperature, or you can say onset temperature, right. Things are changing now. Now TE is extrapolated onset temperature. I will come back to it, why it is important, but for now you can see extrapolated, we are extrapolating, right, because we are drawing a tangent here, then we are drawing a tangent on this curve, right, and where it is intersecting, that is the TE. Tm is obviously, as name is the peak temperature, correct, this is the peak. So Tm is peak temperature, T final is this one, right, where it has now become again flat, right. These are some of the characteristics. Now if we look at the effect of heating rate, right, for an example, see all the like what we discussed earlier, like sample size, heating rate, all that will affect the DSC curve also, because it is basically same, it is not, the response is going to be very similar. In this case you are measuring the heat, right. So if you look at the effect of heating rate on DSC curve, you see, as we saw earlier, as you increase the heating rate, the peaks become broader and deeper, that is what you are seeing here. So 1 degree C, 3 degree C per minute, what is happening? Peaks are becoming broader and deeper, right, is it clear? But what you notice, your peak temperature is changing, but extrapolated onset temperature, if you look at this, it does not change. So that is the usefulness. So efficacy of extrapolated onset temperature compared to peak temperature, because it does not change with heating rate, right. See here, I mean extrapolated onset temperature will be somewhere here, right. Extrapolated means you extrapolate, you take tangent at your this regime, initial regime, and then you draw tangent, right. So there is not much change, obviously I am just plotting this like this, but if you see, but the peak temperature has changed significantly, like this is here, this is here. So there is some usefulness, that is the point, usefulness in using extrapolated onset temperature, because it is unaffected or is not as much affected as your peak temperature when you are using different heating rates, okay. Question is, how do we get this extrapolated onset temperature? So let us look at this plot, right. So you have this exothermic peak for an example, right. So you have this flat region, right, nothing is happening, things are changing. Suppose you decide, okay, this is the point Ti when the slope starts changing, right, your slope starts changing. Now you are in this linear regime, like assume this is a linear part, right. Now you can draw a tangent here. Now you can initially you draw tangent here, so it will intersect at some point. So that can be taken as extrapolated. So it says extrapolated onset temperature. So your onset temperature is Ti, but this is extrapolated. So heat capacity can be calculated, right, because basically we are calculating the power, and if you integrate over if you calculate the peak area, you will be able to calculate the heat capacity. Enthalpies of transitions and transformation, any transformation or transition which happens, right, we can calculate associated enthalpies, because it is basically we can measure the heat, that is the idea. Purity, like if you are talking about the impurity in something, we can see how much is the like we can measure the purity, degree of purity. Chemical kinetics, thermal conductivity, okay. Let us look at how do you calculate heat of transition? Something is happening, right? Something is transforming or transitioning. We want to know what is the heat of transition. So, basically this is a simple equation, delta H is the heat of transition of reaction multiplied with m is the mass of reactive sample is equal to K times A. K is the calibration coefficient and A is the curve peak area. If you know, if you can calculate the area under the peak, okay, for this particular transition, and based on the calibration coefficient you can get for particular instrument if you know heat of reaction of a material, right. So, you use standards where you know what is the heat of reaction, then you can get the calibration coefficient, you know the K. Now, you do your experiments, you calculate A, you can calculate A is nothing but peak area, and then based on the mass you can calculate delta H. So, this gives you heat of transition, right. Measurement of purity we said. So, again see here is an example how, so figure shows the DSC curves for the melting of benzoic acid. So, you see here benzoic acid containing increasing amounts of an impurity. So, you have a benzoic acid, and as we increase the amount of impurity, how it affects your DSC. So, what you see here, C is basically 97% purity, B curve is for 99% purity, see A is for 99.9% purity. See how the purity affects your DSC curve. So, the point is this DSC measurement can be used to assess the purity, right. So, the curve shows an increase in the width of peaks as you are show an increase in the width of peaks, basically the temperature range over which the melting takes place, right, because think if it is not, if it is purer, then the peaks will become narrower, right. So, idea is you can use the DSC curves and get an idea about the purity if you are thinking about assessing its the measurement, right, of purity in your sample. Okay. The third technique which we will talk in this thermal analysis will be thermogravimetry. Thermogravimetry, it is very commonly used. Okay. So, what does thermogravimetry means? In thermogravimetry, we measure the change in mass. In DTA, we are measuring change in temperature between sample and reference. In DSC, we are measuring the heat between sample and reference. Here, we are measuring the mass change as you increase the temperature, right. So, basically we are determining the mass loss or gain depending on the reaction as a function of temperature or time. And this measured mass loss curve can provide information, right, on changes in sample composition, what kind of changes are happening, thermal stability, how stable a sample is, phase is, and kinetic parameters for chemical reactions in the samples. Again, these are the physical and chemical processes which can be studied using thermogravimetry, because there is some mass change. As long as, if you are interested in mass change, then you can use thermogravimetry. So, gas adsorption, desorption, phase transition, right, decomposition, if something is decomposing, right, there is some mass loss, right. So, these are the phenomena causing mass changes. As long as there is mass change, we can use thermogravimetry to capture that. So, weight loss can happen when you have a decomposition, something is decomposing. Simple example one can think of is, this is also one kind of decomposition, right, CaCO3 converting into calcium oxide and carbon dioxide. Evaporation, you are losing moisture, right, loss of volatility. Reduction, desorption, these are the typical processes where you have weight loss. Similarly, you can have weight gain also. If it is, there is oxidation, suppose you have a material which can oxidize, then you will see weight gain. Adsorption. So, these are all physical, these are the processes where you can have either weight loss or weight gain, and as long as there is a weight loss like change in the mass, thermogravimetry can be used. Okay? And obviously these processes are kinetic in a way that there is a rate at which they occur, they will not happen immediately, there is always some, so kinetics plays a role, how fast reaction takes place, right. So that also has to be kept in mind. So typical TG instrument, thermogravimetric, so as we said TG, thermogravimetry, either you say TG or TGA, when you refer to papers oftentimes you will see people using TG or TGA for this technique. So it has basically what does it consist of? So this is a TGA or TG instrument. So basically when you have a sample pan here, next to sample pan you have a thermocouple, because we are interested in measuring temperature, because we are heating the temperature sample and then we are measuring the weight. So you see you have a big component here, thermobalance, it is called thermobalance. You want to make sure that you are able to measure the small weight change, right. So thermobalance is here, you have a thermocouple, sample pan and also furnace. Now you are heating the sample in a controlled environment, right. So there is a furnace and you can purge it depending on the use. You can use nitrogen, you can use other gases, right. For cement we use nitrogen because we do not want it to react with atmosphere. So there is a way to change the purge gas. So what kind of temperature time programs we are talking about? So you can either linearly increase the temperature, so it is like a constant heating rate, temperature is increasing linearly, right, with time, or you could have gradually isothermic. So you are keeping temperature constant, then you are ramping it up, keeping it constant, ramping it up, keeping it constant. Another could be just keep the constant, just go to a particular temperature and keep it there, it is isothermic, right. You understand the difference, right. These are the ways you can change the temperature, the furnace, right. So experimentally what we like, sample size we are talking about milligrams, right, 1 to 100 milligrams can be used easily, and usually for cement we use 20, 25, 30 milligrams, so that is the amount we use. And heating to cooling rate, obviously like it depending on the application, but you can vary it like 1 to 50 degrees C per minute, no issue, okay. In 1 minute you can change temperature up to 50 degrees Celsius easily. Typically we go to 1000, 1100 degrees Celsius. Okay. So when we talk about the mass loss, right, so here we have a mass loss curve. So this is the calcium hydroxide. When what happens to calcium hydroxide? CaOH2, at some point of time it will lose water, right. That temperature you see here up to around 400 degrees Celsius you do not see any change, and beyond 400 C you see change, then nothing happens. So that tells you that there is a dehydration, right, dehydration, it is losing water, dehydroxylation. So if you, why I am mentioning it, we are talking about now derivative thermogravimetry. Derivative thermogravimetry is nothing but first derivative of your mass change versus temperature curve. So you have this mass change versus temperature curve. Now if I take derivative of this, right, derivative will give me this second plot which is here. Basically DTG curve presents the information in more visually accessible form. It is easier to see peaks, right, if you have a couple of, so it is basically there is no new data, you are replotting it, same data, but you are just taking first derivative. Now I can see, okay, up to here it is flat, so I can just measure this, see, okay, I can find out what are the what is the temperature range where it is losing water, right. So it is just gives you more visually accessible form. So whenever you see data in literature or papers, you often see TG with DTG, okay. And area under the DTG curve, another thing is area under the DTG curve is directly proportional to the mass change. If you know, you can calculate the area under the curve, it will give you the mass change, okay. Here is an example of calcium hydroxide dehydration. One example, decomposition, let us look at calcium oxalate monohydrate, calcium oxalate monohydrate, okay, CaC2O4H2O, right. So, it has 3 stages. First it loses water, secondly it loses carbon monoxide, thirdly it loses CO2, okay. So, we will be able to capture that using TGA, that is what it shows. So, when you plot, when you look at the curve, you see first stage where you have a loss of water, second stage corresponds to loss of CO, third stage corresponds to loss of CO2, okay. And this is the decomposition of calcium oxalate monohydrate in nitrogen environment. So, that is the significance or power of this TG. Depending on the reactions, when they occur, right, you will be able to capture it, as long as there is a mass change. If there is no mass change, you will not be able to use this technique, right. If you have a phase transition where there is no mass change, then TGA like thermogravity will not be useful, then you will have to use DTA or DSC, okay. Factors affecting TG curve, right. Again, we are coming back to same, because it is very important to look, pay attention. Heating rate affects your TG curve. Higher rates lead to better defined narrower peaks, but also higher observed dehydration and dehydroxylation temperatures. Sample mass, higher quantities of a phase lead to seemingly higher hydration temperature and to a broader peaks. Furnace atmosphere, that will depend on, you know, the type of reaction. You may have, like cement, may suppose you are using TG for a cement paste and you have a CO2, then you will have a carbonation, CaCO3, right. So, furnace temp. So, these are the things which affect your TG curve. Okay, we will stop here, and in the next class we will go over the application of thermal analysis to study construction materials.